So at the end of our last class meeting, we had defined complex power. I'm going to call this S. And I said that it was the product of an RMS phasor voltage V times the complex conjugate of some RMS phasor current I. So I'm going to make a simple notation down here. So this quantity S is our complex power. And complex power is typically measured in units of volt amperes, where we use the unit volt amperes to differentiate complex power from the average power that we've been dealing with previously, which was measured in watts. Okay. So since our complex power is the product of two complex numbers, it is a complex number itself. And so we can choose to express this complex number in either rectangular coordinates or polar coordinates. So we're going to start with a rectangular representation first. So in rectangular form, multiplying these two complex numbers together is going to give me V effective times I effective times the cosine of theta V minus theta I. So for what it's worth, this part right here is literally just the real part of our complex power S, which we typically refer to as the average power. And the symbol for the average power is typically just the letter capital P. You may sometimes see the subscript AVG for P average, but I'm just going to leave it alone as P like this. And average power, like we've dealt with for power all along until today, is measured in watts. Okay. In addition to this real portion of the complex power, we're also going to have an imaginary portion. And so that imaginary portion is going to be given by V effective, I effective times the sine of theta V minus theta I. So everything but the J is the imaginary portion of our complex power S, and it is typically referred to as the reactive power. Whose symbol is typically denoted as Q, or denoted as Q. And reactive power is measured in volts, amperes reactive, or VARs, in order to be able to distinguish it from the average power and the complex power. So in a more simplified form, we could write this rectangular relationship as simply P plus JQ. Okay. So the average power, or the real part of the complex power, is typically associated with resistance in a load of interest. And the reactive power, Q, is typically associated with any energy storage in our load, either in the form of inductance or capacitance. And whichever energy storage mechanism is dominant is effectively going to wind up giving us the sign on that reactive power term, okay? So if we know that our reactive power is a positive quantity, that means that we have inductance dominant in our system. And if our reactive power is a negative quantity, that means that we have capacitance as the dominant thing in our system. So the sign for the imaginary part of the complex power behaves exactly the same way as the sign of an impedance does in rectangular form, where the reactive part of the complex power is due to the reactive element in our system. And once again, positive sign indicates that we have inductance, and a negative sign indicates that we have capacitance. In polar form, our complex power can be written as V effective, I effective with an angle of theta V minus theta I, where this term V effective times I effective is simply the magnitude of our complex power. So that's the symbol. And we typically refer to this as the apparent power. Since the apparent power is simply the magnitude of the complex power, so it's just the complex power where we throw away the phase angle, apparent power is also measured in volt amperes. So the easiest way to know whether you're dealing with complex power or apparent power is whether or not you have any phase angle that's given to you, right? If there's no phase angle or there's no delineation between real and average, or excuse me, real and imaginary parts, you are dealing with the apparent power. The apparent power is the figure of merit that most electrical systems are designed from, okay? So in a sense, the apparent power kind of represents a worst case scenario because it's simply the product of the magnitude of the voltage times the magnitude of the current without taking into account any phase differences that may occur, which would lower that overall quantity. So whenever we design electrical power systems, we use apparent power as the basis. So typically speaking, you know that your voltage is going to be fixed or something pretty close to fixed. So like here in a residential building or a commercial building, dealing with 120 volt AC system, I would say that largely the voltage that I have access to is going to be 120 volts RMS. And then I would compute my apparent power needs for the whole system and then solve for that effective current. And that effective current is going to tell me what size of the conductors I need to use to implement that power system. And I'll have you guys do that in a couple of your homeworks, and you'll be looking at some portions of the National Electronic Code or Electrical Code, the NEC code, particularly the ampacity tables, in order to figure out what size of conductor to use. Because the size of conductor that you use is dependent on a number of different things, like what type of insulation is used on the conductor, where the conductor is located, whether it's in open air, whether it's in conduit, whether it's buried in the ground, how many conductors are physically located near each other, because there are things called the proximity effect, where effectively there's electromagnetic interaction between the conductors that can cause them to carry more current than you're expecting. All of those things generally need to be taken into account when you're designing an electrical system. So we'll dip into that in a little bit, okay? The angle here is typically referred to, and I'm going to move this over to the side, as the power factor angle. And it's given a symbol theta S, okay? So one thing that I want to bring to your attention, because it is often overlooked, is that our power factor angle theta S is the exact same thing as the angle of whatever impedance our load represents. So just as a quick aside, I'm going to wind up erasing this in a minute, so you actually already have this in your notes. I just want to show it to you. If we look at impedance in an RMS frequency domain system, we would have Z would be the ratio of our RMS phasor voltage to our RMS phasor current. And I can go immediately to the RMS phasor representation because that's the same thing as my simple phasor, except multiplied by a factor of 1 over the square root of 2. But both the numerator and the denominator are multiplied by that factor of 1 over square root of 2, so they cancel each other out, giving us the exact same simple phasor representation that we've dealt with before. Anyway, this would look like V effective with an angle of theta V divided by I effective with an angle of theta I. And so we'd wind up having V effective over I effective with an angle of theta V minus theta I, or simply the magnitude of our impedance with an angle of theta Z. And we can see that theta Z is theta V minus theta I, and theta S, our power factor angle, is also theta V minus theta I. So they literally represent the exact same thing. Okay. So the more simplified form of our polar form complex power relationship would typically be written as the magnitude of our complex power, which is apparent power, with an angle of theta S. Now, I harp on this a lot in my engineering 221 class, but I understand that not all of you took me for 221. So I'm not exactly sure how Dr. Amir handles it or Miss Ward handles it. So I'm going to talk about this a little bit. Realistically, I don't expect any of you guys to memorize really any of these equations per se, okay? Instead, I prefer to think about any complex power system using what's known as a power triangle, and then just compute complex power, and then use my calculator to put my answer in both rectangular form and polar form, and then take what I need from that complex power calculation instead of practically ever bothering to calculate any individual one of these parts directly. Because if I know what the complex power is in both rectangular form and polar form, I know all of this information. So why bother memorizing a bunch of equations I don't technically need? Obviously, I do actually have them memorized because I don't have to bring notes for this, but I don't want you to be forced to memorize a bunch of equations that are kind of pointless if you know how to use your calculator correctly. Okay. So let's talk about our power triangle really quickly. Okay. So the power triangle, wish I could spell triangle, is a simple graphical representation of the complex power that is absorbed by a particular load or supplied by a particular source, okay? So realistically, we're going to see two different types of power triangles in this class, and we'll kind of talk our way through them, but the steps are essentially the same. So let's start with an inductive load. And so I want to quantify what I mean by an inductive load by saying that our resistance R needs to be positive and our reactance X also needs to be a positive quantity, okay? So for a load that meets those specifications, meaning that it has some resistance and some inductance, our power triangle would look something akin to this, okay? So here's my imaginary axis. Here's my real axis. And then my complex power would lie somewhere in the first quadrant, okay? The length of this vector is simply my apparent power. The projection of this vector onto the real axis is my average power. And the projection of this vector onto my imaginary axis is my reactive power. And then lastly, the angle formed by measuring from the positive real axis up to my vector is my power factor angle theta S, okay? So essentially, as long as I can do the mathematical operation that my complex power is equal to the product of my voltage times my current conjugate, If I express my answer in rectangular form, I get my average power and reactive power. And if I express my answer in polar form, I get my apparent power and my power factor angle, right? For a capacitive load, where I have some positive amount of resistance and some negative amount of reactance, I'm going to see that my power triangle actually lies in quadrant 4. So here's my negative imaginary axis. Here's my real axis. And my complex power should be somewhere down here. Okay. Once again, the length of this vector is my reactive power. Excuse me, my apparent power. Sorry for misspeaking there. The projection of this complex power vector onto the real axis is my average power. The projection onto the imaginary axis is my reactive power. And the angle found by measuring theta from the positive real axis down towards my complex power vector is my power factor angle. So we get the exact same relationship. S is V times I conjugate. In rectangular form, we would have P plus JQ, where in this case, Q is a negative quantity. And we would have apparent power angle theta S, where in this case, theta S is also a negative quantity. All right, so before we talk about power factor specifically, I want to show you guys some alternative relationships that we could potentially use in order to calculate complex power. Because sometimes it is annoying to have to know both the RMS phasor voltage drop across our load and the RMS phasor current flowing through our load. So I want to call this part right here alternative relationships. By the way, I know that I'm going through this very quickly because I cover all of this material in my version of Circuits 1. But if anybody has any questions or wants more explanation about literally any of this, please stop me and I will answer your questions. If you don't tell me to slow down, I'm just going to burn through this because I'm considering it a review. But if it's not a review or some portions of it aren't a review for you, please let me know. All right, so all of the relationships that I'm about to derive are based simply on our fundamental definition for complex power. S is equal to V times I conjugate, as well as Ohm's law in the RMS frequency domain, which is simply RMS phasor voltage V is equal to RMS phasor current I times our impedance. So these relationships that I'm about to derive are only really valuable if we know either current or voltage as well as the impedance. If we don't know what the actual impedance is, then we have to revert back to knowing both voltage and current in order to calculate our complex power. Okay. So what I'm going to attempt to do here is effectively just express my complex power S only in terms of voltage or only in terms of current using that Ohm's law relationship. So this is kind of similar to our DC relationship where we had, the power absorbed by a resistor is going to be V squared over R or I squared times R, except now we're coming up with the equivalent relationships in the RMS phasor domain. So let's start by putting everything in terms of voltage, right? So if I start with S is equal to V times I conjugate, well, I'm going to come up with a fraction here that's going to represent I, and then I'm going to take the complex conjugate of this fraction. So using that Ohm's law relationship and manipulating it, I can see pretty easily that I is just V divided by Z. So that would give me an RMS phasor voltage V in my numerator divided by Z in my denominator. Well, as it turns out, when I take the conjugate of a fraction, that's the same thing as conjugating the numerator and conjugating the denominator. So I could rewrite this as V conjugate times V, because the order of operations for multiplication doesn't matter. It's the commutative property of multiplication, if I'm remembering my high school math classes correctly, divided by Z conjugate. What you guys may not remember, and I'd be happy to prove this for you if you want me to, is that whenever I multiply a complex number by its complex conjugate, the result of that operation is simply the magnitude of that complex number squared. It's very easy to see that when you think about the conjugate operation as just changing the sign on the angle of a polar form complex number. So if I had, say, one angle 15 degrees multiplied by one angle negative 15 degrees, those two angles are going to cancel each other out, and I'm just going to have 1 times 1, which is just my magnitude squared. So this is going to wind up looking like the magnitude of my RMS phasor voltage squared divided by the conjugate of my impedance, or just whatever the effective value of my voltage is squared divided by the conjugate of my impedance. Okay. We can do something similar and put everything only in terms of current, right? So I know that my RMS phasor voltage V is equal to just my RMS phasor current I times Z from Ohm's law. So I would have I times Z multiplied by I conjugate, which is the same thing as I conjugate times I times Z, or the magnitude of my RMS phasor current squared times Z, or simply I effective squared times Z. So whenever I'm using my current relationship, I don't have to conjugate my impedance. Whenever I'm using my voltage relationship, I do have to conjugate my impedance. That's probably the most common mistake I see students make, is they forget to take the conjugate of the impedance using the voltage. Okay. So we have these two generic relationships that are valid for literally any impedance whatsoever. But I want to take these now and use them to determine the complex power in terms of both current and voltage for resistors, capacitors, and inductors, so that we can kind of see what roles they play in AC systems. So for a resistance, or for a resistor, and just to be clear here, that means that my resistance is positive and my reactance is exactly equal to 0. Actually, let me move this. That's fine. I'll just keep on trucking down here. We would find that our complex power S sub R is simply going to be, yes. The resistance of the load is positive. So it's like a 5 ohm resistor, 10 ohm resistor, or something like that. It's not negative like the resistance of the ballast for these fluorescent lights. Yeah. So there are no devices that exhibit negative resistance across their entire operating range, but there are some devices that exhibit negative resistance over portions of their operating range. Fluorescent lights are one of those devices. So all negative resistance really means is that if I apply a positive polarity voltage across it, the current is flowing in the opposite direction as I would expect. That happens sometimes when we form plasmas, which is effectively how fluorescent lights work. So literally plugging in my impedance for a resistor into this relationship, I would have V effective squared divided by the conjugate of the impedance of a resistor. But since the impedance of a resistor is purely real, the conjugate is just the resistance value itself. So that's going to leave me with V effective squared over R, or I effective squared times R, which are exactly the same as our DC relationships for the power absorbed by a resistor, which should make sense because the effective value of the voltage is the DC equivalent voltage. The effective value of the current is the DC equivalent current. So it makes sense that we just get our DC relationships. So from this relationship, we can hopefully very easily see that resistors absorb average power in our AC systems. And I'm saying that they absorb average power in our AC systems because we can see that our complex power is always going to be positive and it's always going to be purely real, right? Because V effective is a real number, resistance is a real number, I effective is a real number. So we get just a real portion of power absorbed by any resistance that we see, okay? For a pure inductance, where we have our resistance is 0 and our reactance is positive, okay, we're going to wind up having S sub L is going to be, so this will be V effective squared divided by the conjugate of the impedance of an inductor. So the impedance of an inductor is J omega L. We all okay with that? When I conjugate that, that's putting a negative sign down here. So what does it mean if I have negative J in my denominator? It's the same thing as having positive J in my numerator, okay? If you guys want me to prove that, I'm happy to do it, but simply just multiply 1 over negative J by J over J, and you'll get there in one step, okay? So this is the same thing as negative J times V effective squared over omega L. And another way that this should be positive J over times V effective over omega L. My apologies for that. And if I consider omega L to be the reactance of my inductor, I could write this as J times V effective squared divided by X sub L. Okay. Putting things in terms of current, this would look like I effective squared times J omega L. And just pulling my J out front, this is going to look like J times I effective squared multiplied by omega L, or putting it in terms of my reactance, J I effective squared X sub L, like so. And so from these two relationships, I can see that my inductors will always absorb reactive power, okay? So what I mean by that specifically is we can see that our complex power absorbed by our inductors is purely imaginary. There is no real part, right? So there's not a real part plus J imaginary part. We just have J in our imaginary part, okay? So we only have reactive power when we have a pure inductance, and it should be very obvious to see that I effective squared multiplied by XL or V effective squared divided by XL will always be a positive number because the square of our effective voltage or current is positive. And by definition for an inductance, the reactance is a positive quantity as well. So that's why we have only the absorption of reactive power. Our last case is when we have capacitors or pure capacitors. So I'm going to say that a capacitor or a pure capacitor means that our resistance R is 0 and our reactance X is negative or less than 0. Okay. So in this case, we could say that S sub C is going to be V effective squared divided by, here's 1 over J omega C. And now I need to take the complex conjugate of this. Well, to take the conjugate, I simply change the sign on the J. So I have something that is 1 over negative J. So that's just going to move that negative J into the numerator. So I'll have negative J. Here's my V effective squared. And now I have left over a 1 over omega C, which is the same thing as an omega C in my numerator. And putting things in terms of my reactance, this comes out to be negative J times V effective squared divided by XC, where the reactance of my capacitor is just the magnitude of that impedance, 1 over omega C. In terms of current, we would have I effective squared multiplied by 1 over J omega C, where 1 over J is the same thing as negative J. So that's going to look like negative J times I effective squared times 1 over omega C, or negative J times I effective squared times XC. And here we can see then that capacitors supply reactive power because our complex power in both of these cases is purely imaginary, and it's also always negative. So we've got negative absorbed reactive power, which is the same thing as positive supplied reactive power. All right. How are we feeling? Everybody's catching what I'm throwing. Good deal. So let's talk about power factor as a quantity now. So mathematically, our power factor, PF, is simply the ratio of our average power, P, divided by our apparent power, the magnitude of S, our complex power. If we were to scroll up here and we were to simply take our mathematical expression for average power and divide it by our mathematical expression for apparent power, we would find out that this is simply going to be the cosine of theta v minus theta I, which I'm going to choose to represent as cosine of theta s, our power factor angle, which is why it gets, this is where it gets its name from, okay? So because our power factor is essentially just the cosine of some angle, we know that its value can range anywhere from +1, representing that our average power is the exact same thing as our apparent power, to -1, where our average power is the negative of our apparent power, okay? For the most part, we're only going to be dealing with positive power factors in this class, because a negative power factor simply just means that we essentially assumed that we were absorbing power when we were really supplying power, or vice versa. That's all a negative power factor means, is that we got the direction of our power flow backwards, okay? So when I'm dealing with loads, I tend to always calculate the power factor based on the amount of complex power that is absorbed by my load. And whenever I'm dealing with a source, I tend to calculate my complex power as being supplied by my source. And that will make my power factor 99 times out of 100 come out to be a positive quantity. So let's go through some specific instances and all of that kind of stuff with power factor. And I'm going to start with an angle of 90 degrees, okay? So let's say that our power factor angle, theta s, is exactly equal to 90 degrees, okay? So in this particular case, our power factor would be 0, okay? So essentially what that means is that there is no average power absorbed in our system. Well, this should hopefully make sense, because the only way that our power factor angle will ever be exactly 90 degrees is in the case of a pure inductance, okay? Because we know that in a pure inductance, the current lags the voltage by exactly 90 degrees. So theta v minus theta I will come out to be exactly +90, okay? So in this particular case, we wouldn't consider our power factor to be a leading quantity or a lagging quantity. It's just 0, okay? When 0 degrees is between, or what, excuse me, when theta s is between 0 degrees and 90 degrees, and actually, let me make a note here. Purely inductive load, okay? So when theta s is between 0 and +90, then our power factor is going to be somewhere between 0 and 1, and this is going to be what we call a lagging power factor. And it's because our current is lagging our voltage by an angle somewhere between 0 and 90 degrees. This is representative of an inductive load, not purely inductive, where R is greater than 0 and X is also greater than 0, okay? So essentially, anytime that we see that our power factor angle is positive, but not exactly 90 degrees, we are going to consider that we have a lagging power factor, okay? Coming down, when theta s is exactly equal to 0 degrees, this indicates that our power factor is exactly equal to 1, or we might refer to this as unity power factor, okay? When we have a unity power factor, we are also neither leading nor lagging, because our current and voltage are exactly in phase with each other, okay? So that means that we must have a purely resistive load. When our power factor angle is between negative 90 degrees and 0 degrees, we're once again going to see that our power factor will be somewhere between 0 and 1, but in this case, it's indicating a leading power factor, because our current is leading our voltage due to the presence of some capacitors, okay? So this is a capacitive load where R is greater than 0 and X is less than 0. And our last potential case that we might see is when theta s is exactly negative 90 degrees, which would give us a power factor of exactly 0. Once again, this is neither leading or lagging. And negative 90 degrees occurs whenever we have a purely capacitive load. So, tying things back to our power triangle, we should be able to see pretty easily that if we were to represent our complex power on a complex plane, anytime our complex power, is in the first quadrant, we're operating at a lagging power factor. And anytime our complex power is in the fourth quadrant, we're operating at a leading power factor. Okay? The only time we would ever see a power factor or a complex power in the second quadrant or the third quadrant would indicate that our resistance has to be negative, which again, we're never really going to see cases like that, except in extremely specialized cases, or if we're assuming that power is flowing in the opposite direction that it is actually flowing. So how do you guys feel about the concept of power factor as a whole, or do you need any sort of explanation? All right, so we're just churning and burning through this stuff because it's all review. That's great. So the last thing I want to talk about today then is power factor correction or power factor compensation. I'm just going to write slash compensation here because some people call it power factor compensation instead of correction. Not me, but some people do. All right, so we are going to focus largely on how to make our power factor. So we're going to focus largely on the cases where we have inductive loads. That is largely because while there are capacitive loads that do exist, and there are ways to correct power factor for capacitive loads, those methods typically deal with what are called thyristor valves, and we are not anywhere close to being able to understand how the hell that works. So we are going to limit our discussion here on correcting inductive loads, because we can do that pretty simply by just adding capacitance into our system, okay? So let's consider a case where I've got some sort of inductive load. So here is my imaginary axis, and here is my real axis. My complex power, which I'm going to call S old. So this indicates what our complex power is doing prior to power factor correction, okay? This would have a real part of what I'm going to call P old here on the real axis. It'll have an imaginary part, Q old, here on the imaginary axis. And it would have an angle of theta old here, measured from the real axis up to our complex power of interest. Okay. And for what it's worth, even though this isn't super important right now, it would also have some apparent power, the magnitude of S old, like so. So if we wanted to increase the power factor at which this load is operating, in a practical sense, we would do this by simply injecting some amount of supplied reactive power into our system, okay? That would tend to make that angle theta old smaller. And so our corrected system might look something like this, okay? So here's S new. So we've kept that quantity P old exactly the same because we're only introducing an energy storage element into our system. And so I'm going to just put a dashed line over here like so. This is representing Q new. And this new angle right here is going to be theta new. And it is smaller than theta old. And the cosine of, so cosine of theta is going to look closer and closer to 1 as our angle gets closer and closer to 0. Okay. Now, let me ask you guys a question. And this is something that wasn't actually covered or isn't typically covered in circuits 1. Okay. Is the magnitude of our corrected complex power S new larger, smaller, or equal to our apparent power S old? So I heard one person say it's the same and one person say it's smaller. It's going to be smaller, right? So for what it's worth, our magnitude S, just in general, is going to be equal to the square root of P squared plus Q squared, right? So when P is held constant, that term stays the same. But if we're making Q smaller, then that's going to make our magnitude smaller. So what is the effect, potentially, of making our apparent power smaller in a system? If our voltage stays constant, then that means our current must have gone down. And so if our current goes down, that means we might need, or we might not need to use as large of conductors to electrically excite that load. So potentially this is where some cost savings or something like that could come in, right? If we don't have to have a cable size to carry, let's say 1500 amps of current, we only need a cable size to carry 800 amps of current. That's a significant cost savings because it's going to take physically less copper in order to implement this system, okay? So just something for you guys to think about, why power factor correction can be so important. Not only does it mean the electrical utility pays to generate less power, but the infrastructure cost for supplying these loads is also lower as well. So it's very, very important from a practical standpoint. Okay. So mathematically, essentially what we have is we have a situation where we've got S old, our complex power prior to power factor correction, is equal to P old plus J Q old. And after power factor correction, we have P old plus J Q new. So our capacitor is what's making this transition occur, okay? So we could say that the complex power that is provided by our capacitor, and I'm calculating this as an absorbed power, I want to be clear about that, is simply going to be the difference of S new minus S old. And that would mathematically look like P old plus JQ new minus P old plus JQ old. The P olds cancel each other out, and we're left with JQ new minus Q old, or simply JQ cap, where I just want to make a note here. Q cap is always negative. So this is a way for us to determine the amount of reactive power necessary to correct to some target power factor, PF new, okay? So this is all fine and dandy, but it's usually more useful for us to be able to just calculate the value of the capacitance that is needed to get that result instead, okay? So we have this method for determining the complex power that is provided by our capacitor. And if we look up here, we have this top relationship in terms of only voltage as a way to determine the complex power provided by a capacitor. So I'm simply going to pretty much just set those two things equal to each other and then rearrange to solve for that quantity C, okay, which will tell us what size capacitor is needed. So if I do that math, I wind up with the following relationship, okay? C will be equal to negative Q cap. So negative times a negative number is going to give us a positive, so that we wind up with a positive capacitance, which is important because negative capacitances don't exist, divided by omega, our excitation frequency for our system measured as an angular frequency. And then I'm going to put here the magnitude of the RMS phasor voltage drop across our capacitor. Generally speaking, we would perform our power factor correction across the terminals of our source so that it would correct for not only any inductive load we have, but also any inductance in our transmission lines as well, which tend to cause our power factor to be more lagging, okay? Now, once again, we have a situation where this is perfectly reasonable and correct, but I don't particularly like this relationship because it doesn't relate to our measurable targets, like our target power factor and things like that, okay? So instead, we could write this as P old, which is a constant for our system because it stays the same before and after power factor correction, multiplied by the tangent of theta old minus the tangent of theta new, divided by that exact same denominator, omega times the magnitude of the capacitor voltage squared. This is my preferred form for this particular relationship, simply because if I know what my current operating conditions are, so if I know what my complex power is, and I know what my power factor that I'm operating at is, and I know what power factor I want to be operating at, all of the information that I need is buried inside of this thing. Okay. So it's very, very simple to apply. I'm happy to work example problems about literally any of the tons of different relationships that we've covered today, but they should all have largely been a review from what you did in 221. So if you're okay with not reviewing any example problems, I am too. Whatever floats your boat. Carl, were you raising your hand or scratching your eyebrow? Anybody got any questions, comments, or concerns? Kyle, what's up?
Increase the angle of the power current.
Could you repeat your question, please?
Increase the angle of the power. Can you get the power direction only decreasing that?
So if we were to make theta old larger, we would accomplish that by adding more inductance into our system. That is going to make our operating power factor closer to zero, because the closer our angle gets to 90 degrees, the closer our operating power factor gets to zero. So generally speaking, that's a bad thing. Now, if we have a capacitive load, we introduce inductance in order to correct for that. But that is not usually as simple as just switching inductors in. It's actually a pretty interesting setup. So typically speaking, there are devices called static VAR compensators that are used for power factor correction for both capacitive loads and inductive loads. For the capacitive load side of things, it's either relays that are literally just switching in discrete value capacitors, much like we would simply think about. So like, hey, I need X amount of VARs injected into my system, so I switch on whichever capacitors bring me closest to that particular value. Or it can be a thyristor valve controlled system as well. For the inductors, it's always a thyristor valve controlled system. So effectively, you just have one big honking inductor, able to correct any type of leading power factor that you might have, and you use the thyristor valve and a particular, what's called a firing angle. And that firing angle is essentially related to a duty cycle that is saying like, I'm only going to have the full inductance connected for a specific portion of a half cycle, okay? So you add just like, let's say you might add, 2 Henrys of inductance for, 60% of a half cycle, and that will correct some number of VARs. And if you did it for 80% of your half cycle, it would correct a higher number of needed VARs. So instead of switching in different inductors, it's always the same inductance, and you're just modulating the amount of time it's present in the system to get an average value for your power factor that's close to what you want it to be. And that's a power electronics related thing that you'll learn about much, much later, like ELEN 484, if you choose to take that class in 2 years or so.